WebRTC, short for Web Real-Time Communication, allows real-time communication, voice, video, and data between web browsers. Examples of browsers that support WebRTC include Chrome, Firefox, and Safari. In essence, it's an open-source technology that enables real-time communication between browsers, using APIs and protocols. In practice, WebRTC lets you join web conferences, make voice calls, have video chats, and share files directly from your browser without needing to install any plugins. This functionality is quickly and easily accessible to everyone just by opening a web page. It's also worth noting that WebRTC has been integrated into smartphone apps, where the browser isn't the primary tool. This means WebRTC can be used across different platforms, including computers and smartphones. Some applications that use WebRTC include Google Meet, WhatsApp, Discord, Facebook Messenger, Snapchat, Signal, and Telegram. WebRTC operates on a triangular structure between a server and two WebRTC agents. It works on a peer-to-peer basis, meaning the media streams from the devices are processed directly between browsers without needing a centralized server. The server's role is limited to coordinating the exchange between the two browsers, first to establish and then to control the connection, like managing participants or adjusting video and audio quality based on network conditions. Let's look at how a WebRTC call unfolds. When a WebRTC agent starts, it doesn't initially know who it will communicate with or what the communication will involve. The signaling process begins, aiming to initiate the call so that two WebRTC agents can connect. Signaling uses the SDP for Session Description Protocol to exchange information like IP addresses, port numbers, supported audio and video codecs, connection details, and more. Now that the two WebRTC agents have enough information, they can connect to each other. WebRTC uses the ICE protocol for interactive connectivity establishment to establish this connection. However, peer-to-peer connectivity is made more complex by NAT for network address translation, which complicates direct communication. NAT allows devices on a private network to be assigned a public IP address. If you're unfamiliar with NAT, I recommend checking out my dedicated video on the topic. With the STUN protocol for session traversal utilities for NAT, clients can discover the type of NAT they're behind and their public addresses, making peer-to-peer networking possible. Still, when STUN isn't sufficient, the TURN protocol for traversal using relays around NAT is used. If a direct peer-to-peer connection isn't possible, data is then relayed through TURN servers. Once the connection is established, communication begins. Voice or video streams are transmitted using the SRTP for Secure Real-Time Transport Protocol, a secure version of RTP for Real-Time Transport Protocol. RTP allows the transportation of packets between the devices in the session, particularly voice and video, ensuring that the IP packets are correctly reassembled by the recipient. SRTP functions similarly to RTP, but adds security features like encryption, authentication, and confidentiality, much like how HTTPS secures HTTP communications. Thank you for watching this video. If it helped you, subscribe so you don't miss any future videos, and if you know someone who might benefit from it, feel free to share it with them. See you soon with a new video.